All right, let's jump right in. We're going to spend the next 5 minutes exploring a really clean, minimal extension to general relativity, a new way of thinking where gravity isn't just about mass, but also about information.
So let's start with a big what if. Imagine the universe doesn't just curve because of energy and matter. What if it also curves because complicated states just naturally want to become simpler? That, right there, is the core idea behind what we're calling sheaf physics.
So how do we even get to an idea like that? Well, we have to start with what we already know, with our standard picture of physics, and ask a simple question. Did we miss something?
You know, if you look at any standard field theory, it's basically got two parts, right? There's the kinetic term, which tells you how things move, and there's the potential term, which tells you what states or configurations the field prefers to be in. But what if there's a third piece that's always been there, just hiding in plain sight, the complexity of the state itself? It's called algorithmic information. Basically, how long is the shortest recipe you'd need to describe that state? And for some reason, physics just never included it.
So, to account for this missing piece, we're going to introduce one new player to the game. It's time to meet the z-field.
We're proposing just one new scalar field, which we call xi, and its job is simple. It measures the local description complexity everywhere in spacetime. You can kind of think of it as the density of information, like how many bits of information are packed into a tiny volume. It's an idea that's really inspired by things like the Bekenstein bound and holography.
Now, this new field is governed by a new term that we add to the action. We call it the compression term. And as you can see, it's got two parts that work together to define how it behaves. So this term is kind of like a tug-of-war between two ideas. The first part, the gradient of xi squared, that's basically a roughness penalty. It wants a description of spacetime to be smooth and simple. It punishes complexity. But the second part, the xi log xi term, oh, that's pure information theory. It's the continuous version of the famous Shannon entropy formula, P log P. And minimizing this term, it inherently favors simple, really compressible states.
Okay, so we've added a new field, we've added a new term to our theory. So what? What's the payoff? Well, it turns out the consequences for gravity itself are pretty profound.
And look, the way we get there is nothing exotic. It's the same standard procedure we always use in physics. We start with the good old Einstein-Hilbert action for gravity. Then, we just add our new compression action for the z-field. And finally, we do what we always do. We vary this total action with respect to the metric to find the equations of motion.
And what pops out is this. It's beautiful. We get a modified form of Einstein's field equations. Look, right there on the right-hand side. Next to the usual stress-energy tensor for matter, we have a brand new source term for gravity, coming directly from our information field.
So let's break that down. What does this actually mean? It means the curvature of spacetime, gravity itself, is now sourced by three things. You've got ordinary matter and gauge fields, like we always knew. But now, you also have gradients of information complexity. The actual geometry of the universe is now fundamentally tied to its information content.
Okay, so this isn't just about some fancy new math. This change paints a whole new physical picture of how the universe works.
And this sets up this really cool feedback loop. In parts of the universe where things are algorithmically complex, the z-field gets large. And according to our new equation, that adds positive curvature. That means gravity pulls things together more strongly in that region, which, well, it encourages the system to find a simpler, less complex configuration. It's as if the universe has a built-in drive to become more compressible.
So what about the quantum world? How does this fit in?
Well, if we look at it through the lens of the Feynman path integral, we're told to sum over all possible histories. And in our case, that means integrating over every possible spacetime metric and every possible configuration of our information field, C.
You know, Feynman's big idea was that a particle tries out every possible path. Well, in this picture, spacetimes and their descriptions do the same thing, but they're weighted. They're weighted by how compressible they are. The paths that have the lowest total description costs are the ones that dominate reality. So the upshot is that gravity isn't just emerging from energy. It's emerging from the universe trying to tell its own story as simply and as briefly as possible.
All right, so let's zoom out. What's the big takeaway from all this? What is sheaf physics at its core?
The real beauty of this idea is just how minimalistic it is. We've introduced just one new scalar field. We've added just one new term to the action. That's it. There are no exotic new particles defined, no extra dimensions to worry about. It's just gravity plus compression.
So what we have is a theory that's built on a really simple observation, and it leads to some very clean mathematics. And importantly, it makes testable predictions. You might see its effects in the early universe, or maybe near the event horizons of black holes. It's just an elegant way to connect two of the most fundamental concepts we have, geometry and information. And it just feels right.
Look, this is a framework. It's a starting point. So if this idea sparks something in you, if it gets you thinking, then I only have one thing left to say. Go build it. Thanks for watching.